We will continue the discussion on the Laplace transform with the inverse Laplace transform. You see my full screen PowerPoint slides?
Yes.
Okay. We said that, so now we talked about Laplace and we talked about inverse Laplace. So we can use this to solve a differential equation. For example, if I have a differential equation of this form, what I can do is get x of s as a fraction through the Laplace transform, and then we can use inverse Laplace transform to get the solution, which is x of t. And that captures, so instead of solving this directly, we can use Laplace to do the analysis, and then the inverse Laplace, which can be easier than solving an ODE, and then we get a differential equation. The other possibility is, suppose that I have, let's say, y double dot plus 5y dot plus, remember mechanical systems when we had, let's say, 6y is equal to some, we had the input force or the applied force on the right. So now with Laplace transform, I can get the output-input relationship, y of s over f of s, which is the transfer function. And in that case, it will be 1 over a square, for example, plus 5s plus 1. And using that transfer function information, I can take the inverse Laplace transform and know how will the output of the system behave, y of t, for a given input signal. So that's why we use test signals. For example, if f is a step, then we can easily find the inverse Laplace. Or if f is an impulse, then we can easily find the inverse Laplace, the response of the function y of t. And that will give me how will the output behave for a given input. Usually the input we use as a test signal is the step input, because it's basically in the time domain you're applying a certain number, but in the frequency domain it's 1 over s multiplied by whatever magnitude that you have. So the step input is used for reference signals. Let's say in cruise control we have a reference speed that you want to try, things like that. So it is pretty useful. All right. So here is the solution procedure. So step 1, you apply the Laplace transform to the differential equation in an algebraic equation. Then you solve the algebraic equation for the unknown function and use partial fraction expansion to express the unknown function as the sum of simple terms. And with that, you can use the inverse Laplace transform to obtain the solution. So notice here, what we did is, instead of solving a differential equation directly, we split the process into 4 parts. And each part is not complicated. It's very easy. You're using the knowledge of Math 001 or Math 102. And with that, you solve any differential equation that relates to the context of this class. So here are the Laplace transform derivatives as a refresher. So if I have the derivative of f, then the Laplace transform is s capital F, which is the Laplace transform of f directly minus f evaluated as 0. Similarly, we have the second derivative, we have s squared f of s minus s f of 0 minus f dot of 0. And similarly, you have the third derivative. With that, let's apply the Laplace transform to solve this differential equation. So we had 4 steps, right? Step 1 was to apply the Laplace transform to get an algebraic equation. So we have 0 initial conditions. So step 1 gives me what? Gives me s x of s. So I'll drop, I will not drop anything. Plus 4 x of s equal to what? Can somebody help me with this part? It's 2 over s, right? Exactly, Faisal. Thank you. Now this is step 1. What was step 2? Solve the algebraic equation for the unknown function. So I can manipulate the terms and get x of s So first, let's take common factor. We have s plus 4 equal to 2 over s. I can take this part to the other side. We have s plus 4 here. And then I can raise this, right? Then step 3, use partial fraction expansion to express that known function as the sum of simple terms. Let's go back to the example. Step 3, and we have x of s is equal to, we have two poles here, one at 0 and one at s minus 4. So we have a over s plus b over s plus 4. So let's solve for a and b. Can somebody help me solve for a? What is it equal to? Abdul Wahab, can you explain your answer? What do you mean s plus 4 over s?
I mean, we said like the last lecture. I don't know the name of the method.
Partial fraction.
Yeah, partial fraction. Yeah.
Okay, so we did partial fraction. We have a over s plus b over s plus 4. Now I want to solve for the coefficient a. So a is equal to what? So it corresponds to, so it is s multiplied by x of s, which is 2 over s plus 4. This is evaluated at s is equal to 0. These parts will cancel out. And we will have 1 over 2. Similarly, what is b? Hassan is saying it's minus 1 over 2. Let's verify that. So we multiply by s plus 4 multiplied by 2 over s plus 4. This is evaluated at s is equal to minus 4. These two cancel out. So yes, we will get minus 1 over 2. So we got a as half and b as minus half. So we have here 1 over 2 minus 1 over 2. So now for the fourth step, what was the fourth step? Is to use the inverse Laplace transform. So can somebody help me get the inverse Laplace transform for this part? So what is x of t in this case? Or x of t is equal to what? We have half, just a constant. What is the inverse Laplace transform of this guy? 1 over s. It's a step input. What is a step input? So in the Laplace, in the frequency domain, it's 1 over s. In the time domain, what is it? It's 1, right? for t being greater than or equal to 0. So we need t to be greater than or equal to 0. So for the second part, we have 1 over 2 minus 1 over 2, and we have 1 over s plus 4. So what is the inverse Laplace for that? So you have a shifted e to the power of minus 4t, exactly. E to the power of, minus 4t. So we have a shift in the frequency domain, which corresponds to multiplication by an exponent in the time domain. So any questions about this process? Okay, if you don't have any questions, let's go through it step by step again. So we do the Laplace transform. So the first term is sx minus x0. This is 0, and then we have x for x of t. Then the Laplace transform of 2 is 2 over s. So we have this part. Step 2, you solve for the unknown function. Just manipulate the terms, and you get 2 over s multiplied by s plus 4. So you get a polynomial over a polynomial, which is a rational function. Step 2 done. Then you do partial fraction expansion. This is equal to a over s plus b over s plus 4. A is computed by the following formula. You multiply by s, and then you substitute it as being equal to 0. You get 0.5. Similarly, for the other pole, you multiply by s plus 4, and then you evaluate at s being equal to 0 minus 4. You get minus 1 over 2. So this is x of s. It's 0.5 over s minus 0.5 over s plus 4. Then you do the inverse Laplace transform. This corresponds to 0.5 minus 0.5 e to the power of minus 4t. This is for t greater than or equal to 0. Alternatively, you can do the following: 0.5 minus 0.5 e to the power of minus 4t. And you multiply everything by the step function, u of t, so that it will be 0 when t is negative and 1 otherwise, so that you get the same thing. So let me give you another exercise, and I want you to do this on your own. Let me get the formulas that we need. Just 1 second. So we have these formulas. I'll use some, I don't know, script. So these are the formulas you need. They want you to solve the following differential equation. Can you guys do it? All right. So how much time do you need? 5 minutes? Do you think it's enough? Okay, do you want me to write the procedure too as a hint? Okay, I'll give you 5 minutes. I'll set the timer right now. Please start immediately. And then after 5 minutes, we will discuss. Of course, if you have any questions in the meantime, let me know. I'll be online waiting for your questions or comments. يا شباب. Did you guys get it? Any success? Do you need more time? What's going on? This is an important exercise, شباب. It's one of the most important parts of this unit. Okay, for those who tried it, so what is your answer? Were you able to solve it? Okay, do you need more time? Okay, so I'll give you 2 minutes. You get 5e to the power of minus 2t. Okay, let's see. It's incomplete. All right, so any other attempts? So if you're not able to solve it, what was the source of difficulty? Where did you get stuck? Okay, it seems that people are stuck somewhere, so I'll just... So I'm not going to solve this exercise unless you ask me to do so, or if you have specific questions. Otherwise, I'll just leave it to you to solve it on your own. Muhammad says, solve it, please. Okay, did you try to solve it? Did you get stuck somewhere? What was the source of difficulty? Okay, so Hassan got some expression for the rational function. Okay, then you need to factorize it. Okay, you couldn't factorize it. Okay, let's go through the steps real quick. So what was the first step? Is to find the Laplace transform, right? So how to get the Laplace transform for this guy? We have s squared x of s minus s x of 0, so it's 4, minus x dot of 0, which is 5, plus 3 multiplied by what? X dot, from x dot, which is s x of s minus x evaluated at 0, which is 4, plus 2 capital X of s. This is all equal to, what is the Laplace transform of this guy? It's 1 over s. Now we need to factorize x of s and take common factor and also rearrange things a little bit. So we have x of s multiplied by a square plus 3s plus 2. Then what about the other parts? We have, let me just remove this positive sign. Then we have, so we have here minus 4s. Yeah, this is the only part, minus 4s. Sorry. Then we have minus 5, minus 12, minus 2, minus 17. This is all equal 1 over s. Correct? This gives me what? We have x of s multiplied by s squared plus 3s plus 2. This is equal to 1 over s plus 4s plus 17. We need a fraction here. So this is equal to what? Take s as a common denominator. We have 1 plus 4s squared plus 17s. This gives me what? What is x capital X of s? Capital X of s is the following. We have s multiplied by s squared plus 3s plus 2. Denominator is 4s squared plus 17s plus 1. So this is a strictly proper function, so we don't have any issues with partial fraction expansion. So we stopped here. Now, can somebody help me with the next step? So this is identical to what Hassan got, right? So then we need to factorize it. So what is the next step? Is to factorize. So let me erase some parts here. Any questions so far about this point? How we reached here? Okay. So this is, let me use red. So x of s again is, so let me factorize the denominator. So we have s multiplied by s plus 2 multiplied by s plus 1. This is 4s squared plus 17s plus 1. Partial fraction expansion, we have a over s plus b over s plus 2 plus c over s plus 1. So what is a? So it is s multiplied by x of s evaluated at s being equal to 0. Using this expression, you get 1 over 2, right? Similarly, b is s plus 2 multiplied by x of s evaluated at s is equal to minus 2. So for the numerator, we have 4 by 4, 16 minus 17 by 2. This is minus 18 plus 1, so we have minus 17. The denominator is, you have minus 1 multiplied by minus 2, then you have 2. So this is minus 17 over 2. Similarly for C, C is equal s plus 1 multiplied by x of s evaluated at s is equal to minus 1. So we have 4 minus 17. This is minus 13 plus 1, which is minus 12, over minus 1 multiplied by 1, which is minus 1. This is equal to 12. I put these numbers. A was 1 over 2. B was minus 17 over 2. C was 12. Any questions about this part? Okay. Now, we need to find the inverse Laplace transform. So what is the inverse Laplace transform of these? If it's clear, then what is the inverse Laplace transform now? I have this expression. What is x of t? 1 over 2. This is the step. Minus 17 over 2. This is a shift in the frequency domain, so e to the power of minus 2t plus 12 e to the power of minus t. T is greater than or equal to 0. Yes, Faisal.
Doctor, do we have to multiply by u of t or?
What is u of t? It is 1 when t is positive or 0 otherwise. So you can either state that it is for t being non-negative, or you can remove that and say multiply by t. It's up to you because it's equivalent.
Okay, got it. Thanks.
No problem. That's it for the Laplace transform. You just remove this. Its inverse. Now we move to what's called the initial and the final value theorems. These are important theorems. So suppose I know the Laplace transform of a specific function, and I only care about the initial value or the final value, because if the final value is infinity, let's say, then I don't care about taking the entire function. It's just infinity. There is no reason to care about what's in between, so the system will blow up. Or sometimes I want to know where the system initiated. So there is what's called the initial value theorem, which states that the function f at 0 on the positive side is equal to the limit of s going to infinity of s multiplied by capital F. So the value of the function at the initial time is obtained by taking the limit of s of s, s of s as s goes to infinity. If the function f is not strictly proper, then the initial condition will be unbounded due to the presence of impulse function. The final value theorem is the same thing. So find the final value of the function f. You need to know that you need to take the limit where s goes to 0. So if you want the final value, you take the limit as s goes to 0. If you want the initial value, you take the limit as s goes to infinity. So it's the opposite. There is a condition for this final value theorem to be applicable. The function f has no poles on the right on the right half plane of the complex plane and the right half side of the complex plane, with the possible exception of a single pole at the origin. This is important. So there is an exception to this final value theorem. If these conditions are not satisfied, then you cannot use the final value theorem. F needs to have no poles on the right half plane, meaning that all of the poles are either are negative. If you have one pole at 0, that's okay, but you cannot have, let's say, 2 poles at 0. You only have one pole at 0. And the reason is, so if you have, so if f of s is, let's say, 1 over s squared, if I multiply it by s and take the limit as s goes to 0, then this expression is not going to be realistic. So I can only allow for one s in the denominator. For example, for this function, the poles are s is equal to either -2 or +3. Because of this +3, then I cannot use the final value theorem. This one, I can use the final value theorem because all of the poles are negative and I only have one pole at the origin. So we can obtain f at infinity, but not g as infinity, at infinity. Here are some examples. So I have the function f of s. Now you can find f evaluated at infinity in two ways. One way is to find the inverse Laplace transform. So you use partial fraction, and we have f of t being equal to 2 over 3 e to the power of minus t minus 2 over 3 e to the power of minus 4t. As t goes to infinity, then these terms will vanish, so the function will give me f of t will be 0, right? f of t converges to 0. Now, if I use the final value theorem, I can multiply f by s and take the limit as s goes to 0, and we get 0. Any questions? Okay. Now let's take another example, in which we have a positive pole. So the final value theorem does not apply. But let's take the inverse Laplace transform. And we have 2 over 5 e to the power of t minus 2 over 5 e to the power of minus 4t. Because this is a positive number, f of t will diverge. It will go to infinity as t goes to infinity. But if I apply the final value theorem, which is a wrong application, I multiply f by s and evaluate it at s goes to 0, you get 0, which is not realistic. You see, here we have infinity, and here we have 0. So this is not an accurate result. Why? Because I violated the condition for the theorem to hold. So remember that we can only apply the final value theorem if all the poles of f of s have negative real parts, with the exception of one pole at 0. Yes, Muhammad.
دكتور يعني إذا كان عندنا وحم الأصفار بمقام موجب ما نقدر نطبقها.
Correct.
تمام.
So what if I want the initial value theorem? Can you help me get that? Initial value. So what is f of 0? Let's play with this. What is f of 0 using this expression? F of 0 will be, this is 1, this is 1, so you'll have 2 over 5 minus 2 over 5, which is 0, right? So let's use the initial value theorem. What does the initial value theorem say? It says that you take the limit of f of s as s goes to infinity. So let's do that. What is the limit as s goes to infinity of s of s? So we have 2s over s minus 1 s plus 4. Using L'Hopital's rule, because I have a denominator with a higher order, this is equal to 0. So the initial value theorem applies because it's a strictly proper rational function. So we have different. So here, you can apply the initial value theorem, but you cannot apply the final value theorem because of the positive pole. But if the system has negative real parts, even if it's not, let's say, strictly proper, then you might be able to apply the final value theorem, but not the initial value theorem, because each one of them has certain conditions. Now let's go back to the previous example and apply the initial value theorem. So for the initial value theorem, what do we have? So let's evaluate this at t being equal to 0. It's 2 over 3 e to the power of minus 2, minus t 2 over 3 e to the power of minus 4t. F of 0 is obviously 0. Now, we take the limit of s f as s goes to infinity, and alternatively, you will see that 2s over s plus 1, s plus 4, as the limit of s goes to infinity, this is also 0. So the initial value theorem holds too. So these are very useful and handy theorems to use in order to get the final and initial values of the real-time domain function using the frequency domain representation. Any questions about the Laplace transform and its inverse? Again, we have a homework that is posted for the Laplace transform And we have a test on it next week, inshallah. Okay. If you don't have any questions about Laplace transform, then we can move to the next topic, which is block diagram models. So from block diagram models onwards, we will mostly use the textbook. So far, we've been using handouts because of the contents, but now we can use the textbook. All right. So before we talk about block diagram models, let me just define something real quick. We have what's called the pole zero plot, and this will be very useful for the remaining part of the course. So if I have a transfer function of the following form, I have a numerator and a denominator, then we can plot the poles and zeros using the imaginary plane. So you put x for the poles and 0 for the zeros. So here we have 1, 0 at positive 1. So we have this guy. We have one pole at 0. We have an x here. And we have a conjugate. So we have two x's representing the poles of the system. So we use x to mark the poles. We use zeros to mark are marked with O's. So we show the poles and the zeros of the system using this representation. This is called the pole zero plot of G of S. And the other thing I wanted to talk about is the inverse response of the impulse response of the function. So suppose what was let me recall something here. What was the Laplace transform of the impulse function? Can somebody recall that?
Doctor,
Yes.
is it SF of S minus F naught?
So the impulse function, the Laplace transform of it is just 1. So we have what's called the impulse response. How will the system behave for a given impulse input? So if I give you a transfer function g of s equal to 1 over s plus 5, then it's the same as g of s multiplied by an input, impulse input, which is just 1 in the frequency domain. So the impulse response of the system is equal to g of t, which is just e to the power of minus 5t, with t being non-negative. Okay? This is called the impulse response of the system. So the reason I mentioned the responses here before block diagrams, because you can get systems with a lot of blocks. So we can use block diagram reduction to reduce the system into a single block, which represents the transfer function that captures all of the input-output relationship of the system. And then, given that transfer function, using the response, analyzing the response of the system, using, let's say, an impulse response or a step response, you can know how will the system behave for a given input. For example, the step response of a system having a transfer function g of s is obtained by the inverse Laplace transform of g of s multiplied by 1 over s. Why do we do that? Because usually to the block diagram, to the control loop, is just a number in the time domain, but in the frequency domain, it is 1 over s multiplied by whatever number you have. And we don't care about the magnitude of that number because the system is linear, so whenever you scale the input by a certain number, it will just show up as the output multiplied by the same number. So we take the unit step with magnitude 1 to simplify the analysis. For example, this function is g of s being equal to 1 over s plus 5. So if I have an input to the system, then what I can, and I want to know how will the output of the system behave. So again, what is the transfer function? It is the output y, let's say, over the input, let's say u, right? So this tells me that y is 1 over s plus 5 multiplied by 1 over s. You can do partial fraction expansion, and using the inverse Laplace transform, you get y of t. And that's the step response of the system. Okay, the title here is misleading. Actually, it should say step response instead of impulse response. So there are different kinds of inputs, inputs that we use. One of them is the impulse response, and it is used to test the system and to observe its behavior. Or you can use the step response, which is a good simulation to the applications that we have. And in our control applications that we're thinking about in this course, you have what's called a reference tracking. You have a reference number or a reference signal that you want your system to behave according to, or you want the system to track. So if I know the transfer function capturing the input-output relationship, I can get the step response by multiplying that transfer function g by 1 over s and then obtaining the inverse Laplace transform of g of s over s, which gives me how will the system behave as time as a function of time. Any questions? Okay, so we have block diagrams. What is the difference between step and impulse? Impulse is a signal that is, impulse is like this. Imagine that you have a signal of high magnitude with a small width. This is the impulse, let me just, okay. So the impulse is a signal with high magnitude and small width. So this can be magnitude, let's say, epsilon, and this is 1 over epsilon. And you take the limit as epsilon goes to 0. So it is like you have a shock to the system and you give it a high amplitude for a very short amount of time. It's used in signal processing and in the analysis of signals. The step is as follows. You have a function that is 0 until time is 0, so then it's equal to 1. Just a flat line. This is the difference. So the Laplace transform of this guy is 1, and the Laplace transform of this guy is 1 over s. That's why when we study the response, we take the inverse of g of s directly. For the impulse one, we get the impulse response, or we get the inverse Laplace transform of g of s over s, because we're multiplying by some step input. So that's the difference between the two. All right. So a block diagram is a pictorial representation of a system. It shows different components, subsystems that make a system, and shows their interactions. So it helps us capture a lot of the input-output relationships and what's in between what's in between. For example, if I have just the feedback control loop, and you know the controller, and you know the plant, and you know that you have a feedback, if you want to capture the input-output relationship directly, it can be pretty hard because you only know the subsystems. You don't know the transfer function of the entire system. But using block diagram reduction, I can convert a control loop with multiple blocks into just one block, where the input to it is the input signal, the reference signal, and the output to it is the final output of the system. And that block, if I know it in the frequency domain, it's the transfer function, then I can just multiply it by 1 over s and observe the step response. And with that, I can know how will my system behave for a given input. And then based on that behavior, I know if my system is behaving well or not. And if it's not behaving well, then I can ask myself, how do I design controllers that will make the system behave well? Because that transfer function that will capture the entire relationship will have some parameters showing up from your controller. And you have these controllers to move the system and make it behave the way you want it to behave. Then we have each rectangular block represents a subsystem. Inputs are represented by arrows entering the block, and outputs are represented by arrows leaving the block. So an example, if I have an electrical communication system, I have an input signal to a transmitter, and then we have the communication channel, and we have a receiver, and we have the output signal. So I can make all of these three as one block, and with proper computations, you can calculate it using the knowledge of this unit, block diagram reduction. So a block diagram is used to represent linear relationship between the input and the output of a subsystem. Let the input be U and let the output be Y. So we use U as an input, we use Y as an output. Then the relationship between U and Y is represented by a rectangular block having a transfer function G. So if this is a unit step, then this is Y is just equal to G over S. And if I can know the inverse Laplace transform of it, I get what's called the step response of the system, which captures how will the system behave for a given step input. So here is some block diagram notation. So transfer function block is so every block is a transfer function capturing the input-output relationship to it. So we have an input to this block G, that is X, and you have V. So G is simply V over X, or alternatively, V is equal to G of X. And we have a node representing the summation or subtraction. So the signal entering the sum point is multiplied by -1. In this case for W, because I have a minus here, so it's E is equal to what? E is equal to V minus W. So the output of the sum point is the sum of the entering signals. So it is V plus minus W, so you get V minus W. And we have what's called a pickoff point. So variables connected at a pickoff point have identical value. So the signal here is Y, and you can also think of it as Z here going to the feedback loop, and these values are the same, so Y is equal to Z. So I can take a signal, and even if you give it a different name, it will have the same value because you're just picking up that value in the system. Okay. So with the voltage, for the voltage divider example that we studied before, the time domain, the transfer function is R1 over R1 plus R2. We mentioned that before. So now we might have multiple input, multiple output systems. So how do we deal with them? So you can have U1, U2 as multiple inputs, and you have Y1, Y2 as multiple outputs. So if I have a matrix G representing the input-output relationship, then Y1 is simply what? Simply U1 multiplied by G11 plus U2 multiplied by G12, right? So if I have a vector U multiplied by certain G, then this gives me Y. Correct? Actually, this is GU because of the dimensions. Y is equal to GU. So assuming that G is a matrix, and this is GU. And this can be represented as a block diagram. So you have Y1 multiplied by G11. And you have Y2 multiplied by G, let's say, 21. This is equal to Y1. So it really depends on how you present this matrix. But the idea is the same. So whatever relationships that you have, even if you have multiple inputs, multiple outputs, you can represent it as a block diagram. And this block diagram with the dashed purple line represents the entire block of the system G. Now, we have what's called, so usually we'll have single input, single output systems, but we're showing you this example just to elaborate that even you can capture multiple input, multiple output systems. So now let's talk about block diagram analysis. So given a block diagram with input X and output Y, how to find a single block that represents the transfer function between X and Y. So this is an example. You have G, you have then a feedback loop P with feedback H. So if I want to find the step response of the system, unless I have a block diagram representing one block representing the entire system, it might be difficult. So, but using block diagram reductions, I can replace this guy by a single block, call it, let's say, F, and then I can know that Y is equal to Fx, and if X is a step input, then it's just F over S, and with that, I can see how will the system behave for a given step input easily. But if I don't have block diagram reduction, then things can get complicated and you might need to deal with multiple equations and multiple unknowns. So that's the purpose of this unit. So we'll have some basic rules for block diagram reduction and apply these rules to study the input-output relationship of the system. So what is T in this case? So we'll have multiple rules and we will see how to get it. First, let's study some basic rules. So if I have blocks in series, then we multiply them. If I have blocks in parallel, then we add them up, right? So this block represents this serial combination, and this block represents this parallel combination. If I have blocks in feedback, then the corresponding block representing this relationship is G over 1 plus HG. So I have a question here. Can you guys think of a way to prove this relationship? How do we go from here to here using just blocks in series and blocks in parallel on the summation node? Can you help me prove this? Come on, guys. Any ideas? Okay. So let's say I have an X here and I have a Y here. Okay. Then I have, let's say, some E here. So first, what is Y? Y is equal to E multiplied by G. E is equal to, let's say, this, so I have a pickup point here, so I have here HY. E is simply X minus HY. This is all multiplied by G. Correct? Now this tells me what? Y multiplied by 1 plus HG is, I'm moving this guy to the other side, is equal to X. Hence, Y over X, this is XG, sorry, is equal to G over 1 plus HG. Y is not equal to H. H is the block for the measurement device. So before H, you have Y. Here is Y. This is Y. Then you multiply it by H. Clear? All right. We have blocks in feedback, blocks in series, blocks in parallel. We have also some different rules. So if I have a summation node before a block, then if I move this summation node to here, then I need to multiply x by g. Why? Because before the block, the output here is gx plus y. So we have g, y, but we need to multiply by g. So if I take a summation point to outside the block, then I need to multiply it by whatever it had before going through it. Similarly, if I have a pickoff point, so if I have g and then you have x, I want to move the pickoff point to before g, then I need to multiply by g2. These will help you. These are some tricks that will help us a lot in simplifying and reducing block diagrams into one single block. So again, two blocks in cascade are replaced by a single block whose transfer function is the product of the transfer functions. So GH is just HG here, one block. Parallel combinations are represented by a single block whose value is just the summation of the two functions, transfer functions, G and H. And if I have a summation point after a block and I want to move it to before the block, then you multiply by G, the inverse of G. So this is the same as what we did just now. But here we're moving it afterwards, so we're multiplying by G. Now if I want to move it back, then I need to take the inverse of that. So multiply this guy by G inverse, so you get, it will cancel out. So it's the same thing, but represented differently. So you can move a summation node to before the block, and you just multiply by G inverse. Or you can move it after the block, then you multiply by G. For pickoff points, if you want to move it to before a block, then you multiply by G. Then if you want to move it to after a block, then you multiply it by G inverse. So these are some simple rules that are very intuitive that we will use in order to do block diagram reduction. Again, for a feedback loop, if I had a negative sign here, then we said that this is G over G plus H, GH. So basically you have what is inside the feedback loop, the forward path, the numerator, and you have 1 plus this guy multiplied by the feedback function, and you reverse the sign. So notice here, if this is positive, then you get negative. If this is negative, then you get positive. So the feedback loop is replaced by a ratio of the forward path gain over 1 minus the loop gain. So this is called the loop gain because you have the loop gain is you take a circle, so you have G multiplied by H, and the forward path gain is just G. Next time we will have some examples to elaborate on these ideas, some exercises, and after that we will move to what's called signal flow graphs. So with that, I will stop here. Just let me know if you have any questions. It's almost 12:15, so I'll just pause over here.